All right. Well, if you're watching this, this means we probably had a snow day. So happy snow day, I guess. Um, I'm ready for it to be done. We are starting a brand new unit, so I'm going to intro it very briefly and then get into one of the types of calculations because we can kind of do the math without totally understanding the concept, and then we'll have a greater discussion about the concept behind it once we are back together in class. Okay, so first of all, it's really important to remember that when we have a compound, make sure you can see it, like a simple one like H2O. Okay, what this is actually telling us is that every molecule of water is comprised of two atoms of hydrogen and one atom of oxygen. Okay, the problem is because atoms are so incredibly small. I mean, tiny, submicroscopic. It's too tiny to even comprehend. We can't pick out two atoms of hydrogen and one atom of oxygen and put it together. So anytime there's this reaction, there are beyond billions, beyond trillions of atoms taking part in that reaction. Okay? So we don't pick them out individually, even though that's how they react. We have to have a way to pick them out, either by volume or by mass, is what we normally use. Now, one key concept, and hopefully you have your periodic tables at home. If not, when you have to go to do these calculations, you can look up their atomic mass of these elements. There's lots of periodic tables online. You can just open a window. All right. But if we look at hydrogen, hydrogen has an atomic mass of 1.008. For all our calculations, we're only going to go to one decimal place. Okay. So remember that. That's really important. Okay. We're going to round to one decimal. Okay. If we need to go farther than that, we'll talk about that later on. But for now, on today's assignment and things, we're just going to go to one decimal. Okay. And again, hydrogen has a mass of 1.008, so 1.0. Oxygen has a mass of 15.999, or if we rounded it, 16.0. Okay. So every oxygen atom is 16 times the mass of a hydrogen atom. Okay. Um, so that's really important. If we go from the smallest atom, again, being hydrogen at 1, and the current largest atom is or, organism, I don't know, it's named after a city in Japan, I believe. It has a mass of 294. So one atom of 118 is 294 times as massive as one atom of hydrogen. All right. Well, when we go to do reactions, and again, we wouldn't be dealing with this one, highly radioactive and very unstable, and I think they've only made 4 atoms total. Um, but when we go to do reactions, we measure out in grams, or like I said, volumes when it has to do with gases. And there's some other stuff we'll get into. But for right now, we're just going to worry about the grams. All right. There was a scientist, uh, Amadeo Avogadro. He was Italian. And what he did was he was able to calculate um, the amount of atoms in gases, and they had already come up with this relative mass. The 16, they weren't quite as precise, but they had a relative mass in relationship to one another of the atoms they knew. Well, he calculated out for hydrogen, for example, the number of atoms in 1 gram. Okay. Um, and because he was talking about molecules, and there's some translation stuff in there, the term for that number or that quantity is called a mole, developed out of the word molecule. Okay. And a mole is just a number. You could have a mole of anything. However, a mole of anything larger than an atom or a molecule would probably crush us. Okay. A mole of um, marbles would probably cover the earth several miles up. So So you're not going to have that number because a mole, oh, key concept. Ooh, I've even got a slide. Probably need to write this down in your notes. Title this section, sorry, I should have had you do that from the start. Title this section Chemical Quantities. Okay, chemical quantities, how we deal with quantities of stuff in chemistry. All right, so a mole doesn't really have anything to do with the mole, but looks cool. Is a quantity, a count number, just like a dozen donuts is 12, except it's 6.02 times 10 to the 23rd. And this is kind of like pi. We could go out farther if we needed to. In the college class, we go 6.022. In quantitative analysis, I think it was 6.02214. So you can go even farther if you need to. We're just going to go with 6.02 times 10 to the 23rd. All right. And to write that out, that would be 602. And then because I moved it 2 places, and then 21 zeros. Okay, so to give you an example, this would be a million, this would be a billion. This is where our world population is now. All right, so a mole is more than all the people in the world, but not only that, it's more than all the people that have ever existed, and most likely more than all the people that ever will exist on our planet. Um, because if you took where we're at 9 billion times 9 billion, you'd only get to here. Okay, so even if we squared where we're at, or 8 billion, I don't know where we're at, 8 or 9, we would only be right here. So it's a crazy large number. However, it's so small, the atoms are so small that if you take one drink of water, just a normal healthy drink, and swallow it, there's a mole of molecules in that drink of water, okay? Which, again, if water is H2O, every molecule has 2 hydrogens and 3 oxygens, or excuse me, 2 hydrogens and 1 oxygen, so 3 atoms total. That means you would have swallowed 3 moles of atoms, or think about it, if you go back to the idea of a dozen. If I have a dozen water molecules, I'd have 2 dozen hydrogen and 1 dozen oxygen, except we're just talking about a lot bigger number. Okay? Now, that's kind of the general concept of the mole. We'll come back to this later. Again, this is called a mole. The number itself is actually named after the scientist that came up with it, Amadeo Avogadro. So it's called Avogadro's number. A lot of colleges will have a little celebration in their chemistry department on October 23rd for 1023. Kind of a fun, geeky thing to do. All right. Now, why is this important? Well, what we use this for is we talk about something called molar mass. All right. And that's the mass in grams of 1 mole of any substance. All right. If it's just an individual atom, like phosphorus, for example, I know it's a little hard to read. It's 30.974 grams, or what we're going to use, we round it to 31.0 because the 9 would round up. All right. If it's gold, 1 mole is 196.967. All right. Much, much bigger. All right. So that would be the molar mass for an individual atom. Okay. But for a compound, we have to calculate it by taking the total number of each of the elements, or total number of atoms of each of the elements, multiplied by its mass off the periodic table. And again, we're going to round to 1 decimal. Then you add all that together, and that's the molar mass for that compound. All right. It's also known as molecular mass, or sometimes we just say MM, or gram formula mass, or sometimes just formula mass. We don't even put the gram there, we just say formula mass. Sometimes they just say, what's the mass of this compound? And you would just calculate it, all right? The calculation is fairly simple. If you can multiply and you can add you can do it, and you get to use your calculator. All right. So the first one we're going to do is real simple. We're going to do water. All right. So what we do is we do an atom inventory. So we write down each of the elements we have. How do we know it's an element? Capital letter. All right. Then I use a dash. You don't have to use a dash. Write down how many of each we have. So 2 hydrogen, 1 oxygen. Then we multiply by its molecular mass. Okay. And again, we're going to 1 decimal place. All right. For oxygen, it's 1.0. For for hydrogen, it's 1.0. For oxygen, it's 16.0. Multiply it out. 2 times 1 is 2. 1 times 16 is 16. And add that together now. 2 plus 16 is 18. All right, we use water a lot. So if you can kind of remember that one, that's a really important one, okay? So 18, the way we label it is grams or grams per mole, okay? If we're talking about a single water molecule, the unit would be AMU, which stands for atomic mass unit, but we hardly ever deal with single molecules, all right? Now, let's do one that's just a little more complicated, okay? Let's use, we'll do one with parentheses in it, all right? So we're going to go with Al2, and then parentheses, CrO4, parentheses, 3, okay? So aluminum chromate. And when we do this, we do the atom inventories. We write down each element. So Al, Cr, and O. And then the Al would be 2. Now the parentheses is just like in algebra. We're going to use the distributive property and distribute this in. So right here we have 1 Cr, but because of that, 1 times 3 would be 3. And 3 times 4 for the oxygen will be 12. Okay, you don't add, you multiply in. All right. Then we look up on the periodic table. All right. Aluminum is 26.98, so we're going to round that to 27.0. Chromium is 51.996, so 52.0. And we've already looked up oxygen before, 15.99, so we're going to round it to 16.0. All right, we multiply through. 2 times 27 is going to be 54. 3 times 52 will be 156. And 12 times 16 is going to be 192, I think. Let's take a look. 12 times 16. Bam, 192. All right, and again, 0.0. They won't always be 0.0s. We'll see if we can't take a look at one that is different here in just a second. Okay, so we got 0, 0, 0 is 0. 2 plus 6 is 8, plus 4 is 12. Carry the 1. 5 plus 5 is 10, plus 9 is 19, plus the 1 is 20. Carry the 2. 1, 2, 3, 4. So aluminum chromate is 402 grams per mole. Okay, so if we were doing a reaction with aluminum chromate and water, because of their 2 different masses, we need a lot more mass of aluminum chromate to equal the same number of molecules of water. Okay, so that's one of the ways we can compare them. This formula is much more massive than the mass of water. All right. So that so far should be pretty straightforward. Just a little multiplication and addition. All right. We got one more little part I'm going to stick on it for today, and then I'm going to post a worksheet. If you have a printer and want to print out the worksheet, great. Go ahead and do that. If you don't have a printer, just work them out. You can just go through. I think there's 15 on there. Work them out. Show your work on a piece of paper, and bring it to class the next time we have class. All right. If you get stuck or whatnot, depending on whether we have more snow days or not, you can either email me and I can address it in the next video, or come in early or talk to me in class. Okay. All right. There is a type of compound I want to show you guys real quick. That's called a hydrate. Okay. A hydrate are compounds that have a strong attraction or affinity to water. And what's weird is each compound will combine with water in exact ratios. All right. We can dehydrate them by heating them up a lot of times and forcing the water to go away. And a lot of times the hydrated form and the anhydrous or without water form will be slightly different colors. This is cobalt chloride. It's a very dark maroon color. I'm trying to remember what the anhydrous version is. All right. And then this is copper sulfate. You can kind of tell here, this is the anhydrous form that's white, and they've put a couple drops of water in here and it's gotten dark. It's a really dark blue color in its hydrated form. I will show you some of these in class when we're back. My printer does not do color. All right, so this is cobalt chloride, and then what we do is the water is kind of attached, but it doesn't change the compound. So they put a dot and then the number of waters there. All right, and if you remember, the prefix for 6 was hexa. So we would call this cobalt 2 chloride, okay, because cobalt here would have a charge of 2. So cobalt 2 chloride hexahydrate. And this one down here is copper 2 sulfate pentahydrate because it's got 5 waters, okay? So we're going to take a look at this one, the cobalt 2 chloride, and we're going to do the formula mass for that one. So CuCl2.6H2O. All right. So what you would do, again, you would do your atom inventory. Now, what I like to do, and you don't have to, you could go ahead and do your H's and your O's out. But when you do that, you would need to distribute. The 6 only goes with the H2O. All right. It does not go back this way. So when we do it, we have 1 cobalt, 2 chlorines. But what I like to do, because we do use water a lot, so it's one we can kind of memorize, is we go H2O, and I've got 6 of them because I already calculated that out. That was the first example I did, and we're going to see this a lot. So that's one, probably not a bad idea to memorize it. I think you will just because we'll use it so much, but, you know, go ahead and do that. All right, so cobalt is 58.933. So 58.9. All right. Chlorine is 35.453. So if we round that one, it's going to be 35.5. And our water, we calculated before, is 18. Okay. So when we multiply out 58.9, 35.5 times 2 is going to come out to be 71.0. And then 6 times 18, let's see, that'd be 108, I believe. 6 times 18. Yep, 108. All right. And we would go 9. 8 plus 1 is 9, plus 8 would be 17. Carry the 1. All right, and then 6, well, 5 plus 1 is 6, plus 7 is 13. Carry the 1. So the hydrated form, cobalt 2 chloride hexahydrate, would have a mass of 237.9 grams per mole. Okay, that's how you find the formula mass or molecular mass, molar mass, however you want to say it, for those types of compounds. All right, I will post that assignment. Try and have it done before we meet again in class. And yeah, that's it for today. Be safe. It's cold out there. And hopefully that will do it.